Hi everybody and welcome back. This is example 11.9 as we've been changing the numbers here because I got my numbering system mixed up. That should be 11.9. Shouldn't really matter. It's the problem that looks like this. All right. So this is kind of interesting too. We've got a puck that is moving around, thankfully a frictionless table, so we don't need to worry about that. And it's got a certain radius, it's 20 centimeters or 0.20 meters. And what is keeping this puck in the center? And by the way, I'm going to zoom in here a little bit just so you can see it a little bit better. So I'll mark it up and then I'll shrink it back down again. All right, well, what's going on there? Well, there is a force directed towards the center. There has to be a force directed towards the center, right? That looks like, do I have the right color here? I'll do red. Okay, our centripetal force. But there's nothing actually in the middle holding on to it. Where is that string actually going to? It's going to the other end of that mass right there. It's the force created by the weight of this mass. That is the downward capital mg, that weight that is creating the tension in this string all the way up through it, through the table, all right, and creating the inward pull on this mass right here. All right, or I should say the puck. All right, so what we can say is that the net force on the puck is equal to the tension force in the string, and the tension force in the string is really equal to what? The weight force of that hanging mass, mg. Okay, so this thing is sliding around. It's frictionless. There's no friction between the string and the table or anything. And that inward pull is all because of this downward pull, this mass right here. Kind of like that long pull that we may have demonstrated in class. That is, the weight inside the pole applies the tension force to the string, which keeps the tennis ball moving around in a certain circle. It's very similar to that. Okay? So we can go with this assumption right here to find out how fast this has to be moving such that what? Well, such that this mass right here does not move up or down. Why? What's the significance of that? Let me kind of shrink this back down a little bit more. All right, what speed does a puck need to slide at in order to keep the cylinder at rest? Well, that means that the downward pull of gravity here, in fact, let me change to a different laser pointer, a different pointer. All right, the downward pull of gravity has to be balanced out by the upward pull of tension. All right, so there's just the right amount of tension in this such that it equals this capital Mg right here. And so that's really what we said right here. So the net force, I should say net centripetal force, directed towards the center is going to be equal to capital M times G. All right, I should erase that and do a little C right there. Net centripetal force, okay, equals mg. So we have the mass of this, the big mass, 2.5 kilograms. We've got the mass of the small thing, 1.5 kilograms, and we have a radius. Let's change that radius to 0.20 meters, centimeters to meters is that. So what we want to find is the velocity required such that the inward centripetal force pull is the same thing as the downward the downward pull of capital Mg. Okay, so let's make a few statements right here. The net force on the net centripetal force on the puck is equal to what? We said that just a minute ago. Capital M times G, the weight force of that hanging mass under the table. Okay, but also what's true? The net centripetal force, we can always say this, that it is mass lowercase m, right? Because you're talking about the thing that is being spun around, all right? M times centripetal acceleration, right? ma. This is always true. F is equal to ma, or centripetal force equal to m times centripetal acceleration. So those two statements being true, we can set them equal to each other. Capital Mg equals lowercase m times ac, since those are equal statements right there. All right. Now we're solving for velocity. It asks us what the speed of the puck going in a circle has to be in order to exactly balance out the weight of this, this puck right here? Well, all right, we need to restate the centripetal acceleration in terms of velocity. So capital mg equals lowercase m times, what's our statement about centripetal acceleration in terms of velocity? That should be v squared over r, right? Now, we cannot cancel out the m's because we're talking about two different masses right here. But that's okay, we know them both. So we should just be able to solve for velocity and, or rearrange and solve for velocity. So let's see, this m is going to come down, that r is going to go up, so and then take the square root. So we should have the velocity equal to the square root of r big M g divided by lowercase m. All right, I think I'm running out of room here a little bit, but that's okay. What's our radius? 0.20 meters times our big mass, 2.5 kilograms, times g, we all know that, 9.81 meters per second squared, all divided by the small mass, which is 1.5 kilograms. All right, let's get out our calculators and see what we get. Alrighty, and I get a grand total of 0.57 meters per second. That is our velocity at any one point that the puck has as it's swinging around the table. So it's the velocity at that point right there, that point right there, that point right there, and so forth. All right, 0.57 meters per second. That's it. Thanks for following along. I'll see you on the next one.